Ana Fontcuberta y Morral, and she received her bachelor's degree in physics at the University of Barcelona in 1997. She moved to France, where she obtained her PhD in material science at École Polytechnique in 2001. She then became a postdoctoral scholar in Harry Atwater's lab in Caltech, where she also co-founded the company ANX Technologies. Sponsored by a Marie Curie Excellence Grant, she became team leader of the Walter Schottky Institute at Technical University of Munich in 2005, where she also habilitated in physics in 2009. There, she started her independent research activities in 3.5-based nanowires. In 2008, she joined the Institute of Material Science and Engineering at EPFL and became a full professor in 2019. At EPFL, she is the founder and director of the Laboratory of Semiconductor Materials, and since January 2021, very recently, is the Associate Vice President for Centers and Platforms. Among her recognitions are an ERC Starting Grant, the Emmy Noether Prize in Physics, and the Polysphere Prize, which is a teaching prize awarded by undergraduate students. Please join me in welcoming Professor Ana Fontcuberta y Morral.
Thank you very much, Terry, for this nice introduction. Thanks also for putting together these interesting talks. I hope I can keep you all excited until the end. And I'm very happy to talk with you today about capturing light with earth-abundant semiconductors as a path to sustainable photovoltaics. And I will show you my journey to get to this topic. I will start with less earth-abundant elements, and I will show you how I transition to that in the middle of the talk. I think we all have heard that we need to defossilize our energy systems. And here I would like to show you some recent graphs of a Finnish group. In fact, they calculated what we need to do, so how much fossil-free energy we need to produce in the next years to decarbonize our energy system. And it's quite scary because this is how much we have here left in the next years. So we really need to decarbonize our system immediately if we don't want to increase the temperature of the Earth an average of 1.5 degrees. If they also looked at how you would do it, and this is the proportion of all the renewable energies that one should use, and you see that solar is a very big part of it. So we need to get scalable solar for everyone if we want to decarbonize our energy system. And they also, if you want to look at this report, they also looked at how the different areas in the world can contribute to that with their resources. So the vision here is how can we use this infinite source of energy, nearly infinite for what we can get in the Earth, to create, to help us produce energy to have or continue having our nice quality of life. And can we use it in a way as plants do, but much more efficiently, so to really get a CO2 neutral energy production system. And the question is, what is our role as engineers, as scientists? Can we contribute? And I think we all need to think that in the audience and all around us, we are all extremely bright people, and we should keep every day fixed that we have the duty to contribute to a better world, all of us. And if we all do it, we will really achieve it. And we all contribute in a different way. We all not have to do solar energy, of course. So photonics and PV, this is, I would say, this is a kind of a love story that starts and finishes well. So here is an example of two solar cells. And if I would ask you to choose which one you would like for your roof, I hope all of you would tell me the one on the left, because it's black. So a solar cell should be as black as possible because it should absorb as most as possible the solar spectrum of the light. Of course, you don't see everything here with the black color because we are not able to see the reflection in the infrared and the UV, but basically you would like a material that is as black as possible. And the difference between the right and the left solar cell is texturing of the surface. So people have found very early on that by texturing materials, they can change the momentum of light and change how the light is absorbed in the material. And you can look at these two reviews in which they see different photonic concepts on how you can achieve this in creative ways. One is, of course, texturing, and silicon solar cells have been the first one that were textured to better absorb the light. But there are many other concepts that you can use by either using gratings to change the momentum of light so that you have a very thin film and you're just changing the momentum, you will get all the thickness that, to absorb the light will be perpendicular to the incident light. You can try to use plasmonic enhancers. There's many concepts that you can use for that. And my question was, how can we use these principles to increase the photon collection? And I focused on a different, initially I focused on a different structure, not these thin films and coupling to plasmonics, but I thought, you know, why can we use nanowires, so filamentary crystals that would be standing on a substrate to capture the light? And the reasoning is the following. These kind of structures, like you see here in this sketch, they have been used in different geometries. So going from the left, it would be like a tubular nanowire or a needle-like nanowire or the trumpet-like nanowires. They have been used to enhance a single photon emission for quantum communication. And so the question is, if these are emitters that are very bright, so they're able to let the light escape so efficiently, can we also inverse the process and get them to be very efficient to absorb the light? So the idea here is, can we try to use the geometry of these nanowires to either concentrate light or funnel the light into the wires and get it enhance absorption? And this was the initial questions. And I will first show you an experiment that indicates what the mechanisms are for light to interact with the standing nanowires. So the experiment is as follows. So we put the nanowires in a solution with fluorophores and in a liquid. And then we use a confocal microscope to map which fluorophores are luminescing upon excitation. So you excite your fluorophores in a perpendicular direction, and then you map with a confocal light over the Z with a high resolution of the confocal microscope where light is emitted and where you will excite with a wavelength and detect with another. And so this will allow you to see your incident light, what is the path that the incident light is doing, and how it's interacting with these fluorophores and this high enough density so that you can really map this. If we do this, we obtain the following thing. So here you have, in this graph here, you have the standing nanowire. This is a cross-section in the Z direction. You see it is very bright at the surface of the nanowire. Of course, not inside. We don't have fluorophores inside the nanowire. And then you see that as soon as the light goes through the nanowire, you have an intensity inside. So it looks like the light has coupled in. There is a shadow that develops. So it looks like the photons just go on the wire and then they disappear because they have coupled into the wire. So you create a shadow around it. And you can see the cross-section here on the right, where you see the high intensity of light that is next to the surface of the nanowire. And there is a relatively large area in which there are no photons. They have disappeared because they have got inside this nanowire. So we found this quite interesting. And so we looked a bit more in detail, and we looked at how this light, we excited in different wavelengths to see how this happens for different modes that exist in the nanowire. So here on the right, you have the wave guiding modes at the top, which are just very focused inside, and the ones here on the bottom are the leaky modes that live partially outside the nanowire. So if we look at the absorption that you can calculate for a standing nanowire in these modes, we have that highest absorption is for this one, for the leaky mode, and this would correspond to this peak here. So we went to the experiments and we measured wires and exciting in these wavelengths and corresponding to this absorption curve that you see here. And what you see that indeed, when you are absorbing very highly, is when the light is coupled to these leaky modes. And that's why you have this high intensity at the surface of the nanowire, because the light is propagating through the nanowire as a waveguide, but these are leaky modes, so they also live partially outside. And this is what we are able to detect with the confocal microscope. Intuitively, one would think that the waveguiding modes would be the ones that have higher absorption, because once the light is inside the wire, if it's a waveguide, the light cannot escape from the wire, but this is not what it happens. In fact, this leads to low absorption. And the reason is that waveguiding modes are not easy to couple with. So you come with a plane wave, and these waveguiding modes will not couple well with the nanowire, only the leaky modes will couple well. So learning into this, we decided to try to apply this for solar cells. And so the concept is as follows. We have learned that there are some modes in which the light couples very well to the wire. So you collect the light inside, and this leads into a shadow area around. So it means that the area around the nanowire, the photons disappear. So it means you can have a nearly empty array of nanowires and the light will be absorbed. So we decide to apply this, and this would be the sketch of the solar cell. So you would have a transparent electrode on top and a conductive electrode at the bottom. We started by just looking at a single nanowire solar cell just for simplicity to make sure that we didn't have other factors in just as device fabrication. So we started looking what are the diameters in which we will have this coupling better. So what is the diameter that we should look? And what we have here is as a function of the diameter, what would be the absorption rate when you illuminate this standing nanowire with a 1 sun. And this absorption rate that you have here, it tells you as a unit of a second. And it tells you already that you have few nanowire diameters that are optimal for this. What you need to understand is if this is enough. You're absorbing, it's better to choose a diameter of 380 nanometers than let's say 200, but is this enough, or we're still losing a lot of photons? So to calculate this, we compare the absorption rate with the incidence rate of photons, and this will give us an absorption cross-section. When we look at the absorption cross-section, and here is the diameter for simplification, we can compare the absorption cross-section, so the area in which you are collecting the photons from, with the diameter of the nanowire. What we see is that there's in these high absorption cases, we have absorption cross-sections that are about 3 times larger than the nanowire diameter. So it means that you have your nanowire here and you absorb light all around here because the light is able to couple very well inside the nanowire in these leaky modes, as we said. Now, having calculated this, we knew what dimensions of nanowires we needed, and then we fabricated the device. So the device is a PIN junction. It was deposited on a highly doped silicon substrate, beryllium doped p-type core, and an intrinsic shell and an n-type shell doped by silicon. And so this is an example of these standing nanowires. And then we calculated that we did the device and we illuminated by 1 sun. And what we find here is you have an IV curve in the dark that is typical of a diode. When we illuminate, you create a photocurrent. If you normalize the photocurrent by the cross-section of this nanowire, you will get something like 180 milliamps per square centimeter. This is just humongous. I mean, it's very big. The best solar cells, single junction solar cells, will have something like 30 milliamps per square centimeter. So here it doesn't mean that we get a fantastic solar cell. It just means that we are collecting light not only on the top of this nanowire here, but from a region that is much larger than this. And that's why we get this very high current density. We then converted we did a spectral response and calculated how many photons, so how many electron hole pairs we get per incident photon on the cross section, and we compared to a nanowire that is lying down of the same batch. And what you see that when it's lying down, the response is much lower than when it's standing, which is what we are expecting. We also see that close to the band gap, and that's where the absorption coefficient of gallium arsenide is the lowest. We get 15 electron hole pairs created by every nominal photon that gets into the nanowire. And again, the reason is because you not only connect the photons that normally they arise on the top of the nanowire, but also all the others around are contributing to the photocurrent. So this was a demonstration that this principle works. So we collect about 15 times more photons overall. So where does the field stand today? There were other groups that also understood that you need to optimize the distance between the nanowires and also the diameter. So parallel to our paper, the people in Lund managed to make an array with an efficiency of 13.8%. And later on, they achieved 15.2%. And the people of TU Eindhoven and Amolf, they demonstrated a higher efficiency. And not only that, but they demonstrated that in fact, and it's what our paper said, is that these wires, they concentrate the light, and so they work under concentration. And this should help also to increase the open circuit voltage of the device because of the concentration effects. And in fact, they demonstrated in Eindhoven that in fact this is the case. You can increase the open circuit voltage, and this should allow you to obtain even higher efficiency than in a normal solar cell with gallium arsenide. So this is where the field stands today. So you can try to think about this concept and go beyond. And the first thing that one thinks about is multiple junction solar cells. And the easiest one would be think about a bottom cell, traditional bottom cell, and put your nanowire solar cell on top and see what material combination gives you what and what is the efficiency you can get. You can connect this in series, which means that you have to match the current that is photocurrent that is created on the top and the bottom. And you can see here the maximum efficiency is about 40% that you can get, depending on what material you put in the bottom. So you should get a material that is a bit higher bandgap than germanium, and you would get this very high efficiency. You are much more free if you have a four-terminal solar cell in which you connect the current at the photocurrent at the top and at the bottom independently. If you do this, you're much more free of what material you want to use at the bottom cell, because one compensates each other, and then you can get also a much higher efficiency. So this would be my recommendation. You can even get the silicon as a bottom cell and get a very high efficiency. So in principle, what this means is you can have a typical silicon solar cell, and you can put on top a nanowire array solar cell that would collect the current independently, and you would increase the total efficiency by a high amount. Using the same photonic concept, you can even get more crazy and creative. And this would be what we thought. So in fact, because we are collecting the light from a much larger region, we could think about a multiple junction solar cell in which the materials, they don't have to be on top of each other. In fact, they can be next to each other, and we will just collect the light at different heights by just regulating the length of the nanowires. That's what you see here on the left. So you see nanowires of different band gaps and different lengths. And so the thinnest one would be collect like the UV photons, and then going to the shorter wires, they would collect redder and redder photons. So if you do this, you can just have the wires next to each other, and you need to find a way to connect them independently, depending on the type of material you have. This is possible. Of course, it's complicated from the device point of view, but it's not more complicated than what you have in your computer. So if you do this, then you would get about 48% efficiency, and you would save about 1,000 times in very expensive materials, which are the 3,5s. Just for the note, growth of different kinds of 3,5s or nanowires on a subset, this has already been achieved by a few groups. So now I would like to share with you the rationale to go beyond photonic concepts and to make really an impact in the photovoltaic arena. So if you think about the best solar cells, single junction solar cells, you would think about gallium arsenide solar cell, very expensive solar cell. So if you compare this, this would, if you want to cover your roof with that, it would cost the equivalent of a very expensive car. Now, if you, instead of having bulk gallium arsenide, you would go to the nanowire solution, you will diminish the price by about, let's say, a factor 1,000. So it would be the price of very beautiful earrings. So a bit more easy to buy for most of us. But now, can we go a step even further? Can we decrease the price by a further factor 1,000? And can we make these solar cells at the price of what you spend per week to buy your food? So this is the rationale to go, and can we push this to the limit to make it really, really cheap and as functional as gallium arsenide? To go this, we need to think about what is the maximum theoretical conversion efficiency in a solar cell and how it depends from the band gap. And so here is the typical Shockley-Queisser efficiency curve in which you see the maximum you can get in a single material solar cell, and also what materials we have depending on the band gap. In blue, I have compound semiconductors that are made of material of some elements that are not very abundant on the Earth crust, so that's why they're expensive. And in orange, you have materials that are made of elements that are earth abundant. You also see silicon. Silicon is very earth abundant. One inconvenience of silicon is that silicon solar cells have to be of a certain thickness, because silicon is an indirect bandgap semiconductor. And this means that you have to purify silicon a lot, and this is very energy intensive. So this would be the inconvenience of silicon, and we try to go beyond that. So knowing this, we have here a few candidates, and we would have, for example, copper sulfide, and we notice that copper sulfide exists in two compounds. So, and these two tend to decompose from one to the other. Much more stable is zinc phosphide. So I will show you our results on zinc phosphide, which is what we chose as a material. You can also, other arguments to convince you about that is to look at the abundancy. And in this graph here, you have the capability of the different photovoltaic systems to provide energy if they were working at the maximum theoretical efficiency, given the current production on the elements. And so you see here on the right, you have the maximum, materials that can give you the most efficiency if you were able to invest in them, given the production rate that we have in the mines today. Another way of plotting this data is to plot the material extraction cost index and also as a function of the annual electricity potential index. So this gives you a sense of, if you invest in a material, how much electricity this can give you, and so how much is this worth. And from these quadrants, the quadrant that is worth is in fact these materials here. And we have concentrated on gallium arsenide. I have shown you that by doing nanostructures, we can put this up. So we can, with the same material extraction cost index, we can increase the annual electricity potential index, but it is not enough to go put it in this quadrant here. So now what I will show you is what we can do with zinc phosphide, which is in this top quadrant here. So for this, zinc phosphide has a band gap that is direct at 1.5 electron volts. And earlier work showed that it has a good minority carrier diffusion length, and the absorption coefficient has been shown to be quite high. So it's a good candidate for photovoltaics. The challenges is that there is no substrate to grow it on. There is no substrate, commercial substrate available who has the same lattice constants or composition. And so also the thermal expansion coefficient is very different from any other materials. So it may be that you have some issues with the epitaxy, and I will show you today what we do to circumvent this. To circumvent this, in fact, we use two strategies. One is to nucleate the material at the nanoscale. If you nucleate at the nanoscale, you can really get rid of the lattice mismatch and the structure mismatch, and also the mismatch in thermal coefficient. If you also grow on graphene, you have van der Waals bonding, and you also get rid of all these. So either you have your material grown floating on the graphene or nucleating it at the nanoscale. For these, we use molecular beam epitaxy. So just in a nutshell is the ultra high vacuum technique. You have your sample here, and you evaporate controllably all the elements. And this is a way to understand how to produce a very high pure material and to evaluate its potential later on for commercial use. Starting with the van der Waals epitaxy, here we use commercial graphene on oxidized silicon substrate, and the advantage is that it doesn't have any covalent bonds with the material, and so you can nucleate in defects of the graphene, and then it will grow laterally, and there will be no defects due to the lattice mismatch. So this is the mechanism that we pictured, and so because it's commercial graphene, you will have some grain defects indeed, and this will be the nucleation points where you will start creating some seeds, and then a material will just grow laterally to form thin layers. This is an SEM of the initial stages of growth of these crystals. You can see that some of them are oriented in the same direction, which means that when they grow, they just merge together, forming a single crystalline film. In small regions of the substrate, of course, as a whole substrate, you will have a polycrystalline material. So if you look at it, it looks a bit awful. So when you look at this, you would think that this is not going to work. But when looking at the optical properties, we see that this material is emitting light, which is one of the requirements to have a material that can work as a solar cell absorber. So then looking at the nanoscale, our idea here is to nucleate at a very small scale to avoid defects that you create when you have a thin layer growth, and also to avoid the effects of the different thermal expansion. The first thing we tried is what is called vapor-liquid growth, where you start with a metal droplet that will gather all precursors and nucleate the axial growth. And so what we use is indium zinc droplets that gather the zinc and the phosphorus, and they create a nanowire at the end. We were able to do it relatively promptly, and these are the different morphologies that we were able to obtain depending on the growth conditions we were using. And this is an example of a very good control of the vertical morphology, which is what you need to create a solar cell. And this was obtained by just controlling the fluxes and temperatures very precisely, which is what molecular beam epitaxy can give you. So the next thing that we looked is that, which is quite interesting because other compound semiconductors don't have this, is that we noticed that by changing the growth conditions, we can also change the composition in the compound, which is a bit counterintuitive for compound semiconductors. So here shows how, depending on the growth conditions, the fluxes of the group 5 and the group 2, the zinc and the phosphorus, we were able to obtain different compositions in the nanowires. Interestingly, all of them are light emitters, and this was tested by cathodoluminescence. This is a scheme of the cathodoluminescence apparatus that we use. And what we see is that by changing the fluxes, we're able to change the emission by a large amount, which is still, the reason for that is still unresolved, because in principle, only the stoichiometric Zn3P2 should be emitting. So we are now trying to understand what's going on in the material, why we have a good emitter, and why we can tune the light emission so largely. We also looked at the absorption coefficient in a different way. And for this, we collaborated with Ilaria Zardo from Basel. And she created an experiment in which she has a nanowire hanging here, in which he excites. And he measures the absorption coefficient by looking at the heating that she creates through the wire into this suspended thermometer here. By doing this, we compared the gallium arsenide nanowires with similar dimensions and the zinc phosphide, and we see that there is about a factor 5 higher in than gallium arsenide. So zinc phosphide absorbs light in this range of energies about 5 times more, which again is a good thing for solar cells, so we can even be better than gallium arsenide. We then went on and looked at other ways of growing at the nanoscale. So starting with a pattern substrate with very small holes, we started to understand how the growth would grow there. The initial hope would be to grow vertical nanowires in localized space, but we understood that there's something else that happens. In fact, when you let this thing grow as a function of time, you see how you start creating some pyramids instead of standing nanowires. And this is at the end of the growth. And then if these holes are close enough, you will create a textured film. So by growing at the starting growth at the nanoscale, you're able to create a thin film that is completely textured and ready to work as an absorber in a solar cell. And so if you look at the TM, you will see that these are really single crystalline materials. And so it's quite interesting that the nucleation at the nanoscale allows you to have a textured thin film that is nearly monocrystalline. You have here some joint grains between the pyramids, but when they merge, they really create this nanostructured film that has extremely good optical properties. So here is an example of what you can do. So we can tune the composition again, depending on the nominal hole size in which we start growing. Here is an IV curve of these zinc phosphide layers grown on intrinsic N and P-type substrates. And we see that when we grow on an N-type substrate, we have a diode indicating, and in P-type substrate, you have a more like, not a Schottky junction, it's a nonlinear IV curve, but more resistive than Schottky-like. So it means that our material is zinc phosphide is P-type, which is in agreement with literature, and we can create PN junctions that would work as a solar cell. So this is where we stand today. We also saw that these textured thin films emit light, and you see here on the right the emission from the zinc phosphide at the band gap, and this is much better than what we observe for the growth on the nanowires and also the growth on graphene. So we are now thinking that this will be the way to get the zinc phosphide as the next generation material for solar cells. So as a summary and outlook, so hopefully I have convinced you that photonics and material science approaches can help us tackle sustainability issues, that nanostructures provide a new way to save resources, but also not only because of the size, but because of the photonic properties, and that this will help us tackle energy issues. And I have provided you some examples. So I need to thank my students. They are the ones working very hard in the lab. Also my postdoc, Mira, who just joined, and she's putting a lot of energy in these new materials, and the funding, and you for your attention.
Thank you, Anna, for the beautiful talk and inspiring message, and how we can, use our problems to all contribute to something bigger. Thank you for that. That was beautifully articulated. So just as a reminder for those asking questions, if you have video and audio access and wish to ask a question, just activate your video and unmute your audio so I can call on you and the rest of you to insert your questions in the Q&A. So I guess I'll start off with the first question related to the vertical growth, the first half of the talk. So at the end, you mentioned that you could change the height as well as the diameter to access RGB colors. But I was wondering whether there was any optimization at a particular wavelength so that you could avoid the shadowing effect. So for example, if you shrunk in the vertical direction, can you ever get it so it's more, so it's more absorption for the entire structure versus concentrated at the top compared to the bottom?
Mm-hmm. Yeah. So in fact, you observe too. In fact, I didn't show this, but if you look at the FDTD simulations, in fact, the light enters the top, so it couples in, but then it stays back and forth from the substrate. So if you look at the FDTD simulations, the intensity of light is quite homogeneous through the length. So you're not, even though it's coupling at the top, it's still homogeneously distributed through the length of the nanowire. So.
Oh, I see.
Yeah.
Okay, great. From one person, exciting work, but will it ever be competitive with silicon PV? Are there concepts to improve silicon PVs using metamaterials?
So one concept would be, because these nanowires can be, in fact, you can embed them in a polymer, and you could embed them in a polymer that is conductive. So you would be able to peel off these wires, and people have done this. So the idea would be to have this array of wires embedded in a polymer with a conductive top and bottom, and you would be able to put this on a solar cell at the top. Of course, you need to work on the anti-reflective coatings of the silicon solar cells. It's not just putting on top, but in a nutshell, the vision would be this, to just have these flexible cells with the nanowires that you put on a silicon device.
Thank you. Corey?
Hi, Anna. Great talk.
Hi.
Nice to hear from you. So I'm really struck by your second part of your talk, where you were able to grow, zinc phosphide using, Waals epitaxy. So I think that essentially lifts the restrictions on, like, you can pretty much grow any material. Right now you're focusing on zinc phosphide, but I assume that you will be able to grow gallium arsenide. So I think there's a significant advancement in that material science part. So my question is, you have shown this textured materials. So did you do like detailed studies about the defects that might occur during the growth, or and then one thing that you mentioned is that the absorption coefficient of zinc phosphide is much larger than gallium arsenide. So do you know why the reason might be?
Mm-hmm. So this texture growth is quite useful, and we plan to expand it to the family of these zinc phosphide materials to really cover other band gaps and to think about also more than single junctions. And why the absorption coefficient is much larger is it's due to the band structure. We also have calculated the band structure, and it turns out that the conduction band is a bit more complex than typical materials. There's several conduction bands on top of each other, and this creates a lot of transitions that are available for the range of wavelengths that we are interested in.
Okay, thank you.
So can you speak to a little bit the manufacturing challenges, whether they, you have these beautiful, amazing images of the structures in the lab. Are they easily scaled to be integrated with commercial technologies?
So right now we use molecular beam epitaxy because we wanted to understand how to produce, what their limits are on the production of this material, how much can we vary from the stoichiometry to get good material results, and this tells us about the scalability. I think at the end we will have to produce this with sputtering. Probably sputtering will be the scalable technique and not molecular beam epitaxy. Molecular beam epitaxy is just a research tool. Now, I think that nucleation at the nanoscale is still important, and for this, I think the way to go is with nano imprint. Our holes don't have to be too small, So even with a stepper technology that you can go to really high wafers, you can use it. So we're looking at stepper and nanoimprint technology to really scale this up.
Great. So how does the mechanical durability of your nanowire-based PV compare to conventional ones? For example, do the vertical nanowires become damaged if you try to pull them off or transfer them to a different substrate?
They are very difficult to break. Of course, they will break at the base if you scratch, but otherwise they're mechanically very, very stable. And this is because they have no defects. So, but this has been shown by mechanical engineers, that the mechanical properties are superior than bulk, and this is due to the small size and because of the lack of defects. So fracture happens when small defects in materials, and there is no defect, so there is no way to break them. And people have shown in numerical experiments, and we see it also.
And speaking of other types of robust properties, how does the robustness of the zinc phosphide compare to other types of either gallium arsenide or silicon wires for light absorption? For example, if you're trying to think about integrating them later in different climates and environments.
So the surface would be, when you take it out of the reactor, the surface will react with the ambient water that you have in the atmosphere, but it stops. So just the first monolayers react, they create a native oxide, and then it stops. So in the past, people said that it reacts with water, but it's just the first monolayers, and this you can remove with a chemical oxide when you process devices. So it's relatively similar to other compound semiconductors.
Great. Okay, any other last questions? We have just a couple of minutes. I didn't want to cut anybody off. Okay, well, thank you for a fantastic talk. I appreciated that very much. So before we close the webinar, I'd again like to thank all of our distinguished speakers and their very inspiring presentations, and also for their willing to be up late and later to share their work with us. Thank you for joining us for this Frontiers in Nanotechnology virtual mini conference. There will be more in the coming weeks. So if you're subscribed to our emails, you will see them. And more information will be found on the ION website, inano.org. So thank you again. And depending on your time zone, have a good afternoon, an evening, or morning. Thanks for joining us.